Right, this lesson all about buffers. By the time we're done, you're going to identify the components of a buffer solution. You're going to be able to determine the initial pH of a particular buffer given its components. And you're going to be able to calculate the pH of a buffer after you have added strong acid or strong base. All right. So, why buffers? So first of all, what is a buffer? A buffer is simply a solution that is designed to be resistant to changes in pH. So if you add a strong acid or a strong base, the hydronium or hydroxide concentration, the pH, of this buffer solution doesn't change. So why is that important? Well, because a lot of biochemical processes are incredibly sensitive to solution pH. In fact, blood is buffered to pH about 7.35 to 7.45, so it's a little on the basic side. And this actually is so critical that there's actually two buffer systems in blood to keep it to such a narrow range. In fact, if the pH drops below about 6.8 or rises above about 7.8, that's pretty much it for you, so don't do that. So let's talk about how you would make something resistant to a pH change from the addition of acids or bases. Well, you know that the key is neutralizing, and so to neutralize an acid, you need a base around, and to neutralize a base, you need an acid around, and in biochemical systems, both of these scenarios are likely. So you want to have both some acid and some basic species present in the solution. Now, remember this, in this case, that solution is in fact you. So you'd want some around, and why not, have the strongest acids or bases acid or base you can have in water, namely hydronium and hydroxide, around. Well, the hint is kind of in how I actually drew this, or how I wrote this out. That, remember, the concentration of hydronium and hydroxide specifically in aqueous solutions are not independent. And they are linked by the autoionization of water, and that equilibrium constant is about 1 times 10 to the negative 14th, which means you will never ever be able to have significant amounts of both of these in any aqueous solution. You can have a lot of one, or you can have a lot of the other, but never a lot of both. In fact, in a previous video, we determined that if you want to have equal amounts of them, that is only possible at 1 times 10 to the minus 7 molar. That's a very low concentration, so you're not going to be able to neutralize a lot of acid or base coming into your blood for whatever reason. And the solution around this actually is to use a different acid-base system that is not linked by that equilibrium, so you can have arbitrarily high concentrations of both an acid and a basic species. So in the next slide, we'll talk about kind of how that works. But first, so let's talk about unbuffered solutions. So we're going to define an acidic solution as one where there is more H3O plus than there would be in pure water. And we're going to define a basic solution as one where there is more hydroxide than you would find in pure water. And as an extension of this, if it's an acidic solution, there's more hydronium than hydroxide. And if it's a basic solution, you will have more hydroxide than you do hydronium. Okay. So let's talk about what happens when you add a strong acid, for example HCl, into an aqueous solution. Well, this happens. So HCl, which by itself at room temperature and pressure is a gas, actually reacts with water to form hydronium and chloride. And because this is a strong acid, this is not really an equilibrium, the reaction almost goes to completion. So we could say something along the lines of, if 1 mole of HCl is going to produce in that solution 1 mole of hydronium, and the pH will change accordingly. On the other hand, let's talk about a strong base, the prototypical strong base, sodium hydroxide. And when sodium hydroxide, when you dissolve it in water, just going to fix this now. Yeah, it's a solid. It dissolves or dissociates into sodium ions and hydroxide ions. And again, this dissolution is essentially complete, which means that 1 mole of sodium hydroxide will give you 1 mole of hydroxide ions in solution, and again the pH will change accordingly. Alright, so and the key is to use basically a weak acid base system, basically a weak acid base conjugate pair. So let me explain how this actually works. And the ground rule is, so here's a thing that you need to know. An acid will preferentially react with the strongest available base in any solution. And conversely, a base will react with the strongest available acid in the solution. So this example here, these two slides talk about the weak acid-base pair. Specifically, this is acetic acid vinegar, and this is its conjugate base, acetate. And this hypothetical, so this bar here represents the concentration or the amount of either one of them. And in this case, we're starting with a solution that has equal amounts of both of them. So how does this work? Well, these are the reactions that are sort of going on here. So if let's say that you add that somehow an acid gets added to this buffer system, and we're just going to generically call this hydronium. It's going to react with the strongest available base it can. Now, there are two possibilities actually. So what's floating around in solution? There's a lot of water, there is the acetic acid, and there is the acetate. So, and which is the strongest base? Well, it's probably not the thing with acid in its name. So you've got the choice between water and acetate. This acetate is the conjugate base of a weak acid, so that tells you that it itself is a weak base. But it's the strongest available base. It's still a stronger base than water. So it's going to react, and there'll be a proton transfer from the hydronium to the acetate to form a little bit more acetic acid and consume a little bit of the acetate. So now their ratios have changed. We have a little bit of excess acetic acid and we have a little less acetate. The other thing that is important to know is that anytime an acid-base react, as long as one of the pair is strong, you can assume that reaction goes to completion. So in this case, hydronium is a strong acid. And you will note I have a reaction arrow and not an equilibrium arrow here. So this reaction essentially goes to completion. Now, if you were to add hydroxide, let's see what happens. So the idea is that this is a strong base, and it's going to react with the strongest available acid. Again, the choices are the weak base, acetate, the water, or acetic acid, so go with the thing with acid in its name. And what's going to happen? So it's going to rip a proton away from the acetic acid, which means that you're going to make a little more acetate, and you're going to consume some acetic acid and make a little more acetate. And here's that reaction. Again, one of the pair, the hydroxide, is strong, so you can assume it goes to completion. So what have we done here? Well, we have essentially traded a strong acid, the hydronium, for a weak acid. And we have traded the strong base, hydroxide, for a weak base. Pretty much quantitatively, these reactions occur, again, almost to completion. Now, this is an acid. It itself will react with the hydronium to make some, with water to make hydronium, but so much less. It's a weak acid. So, instead of, so for every million hydroniums you put into the solution, you will make a million acetic acid molecules, and maybe of that million acetic acid molecules, one of them will go on to form a hydronium ion. So It's a trade-off of almost a factor of a million, and it's a similar idea here. You are trading off a strong base for a much, much, much weaker base, which has a much lower effect on the solution pH. So the other thing to note, and we'll crunch the numbers on these, um, the addition of acid or base to a buffer does actually change its pH. It's just by a much, much, much smaller amount.